up with all your emails. Thank you.
Thanks for that nice introduction, Sue. And thanks for having me here, and giving me the opportunity to present and the willingness to reschedule to because of weather the first time. So I'm really happy to be here. I'm really happy to be here today. I mean, it's wet out, but it's not like sheet of ice and 10 below like it was earlier. I'm an Okie, so I'm not made of stern stuff when it comes to cold. Yeah, I want to give, Sue did a nice job of kind of introducing me, so I'll do the kind of 30,000 foot view. This is the thick, stuff from my basically CV. But the important part is, yay, Oklahoma. I'm an OU grad, School of Meteorology, and with a minor in math. Then I went up to Seattle for 5.5 years, and met my lovely wife, Elizabeth. Not wife at the time when I met her, but she became my wife. And then back to OU, Oklahoma, the joint NOAA Institute there for about 8 years. And then I've been here in Lawrence for 17 years now, coming up on 17 years now. So I've been very happy to be here. Grew up from a wee assistant professor through the promotion cycle, and I'm chair of the department. I'll accept your condolences on that. Okay. Okay, so this is sort of the formal, stuffy part. As they say in Oklahoma, this is my bona fides. As an undergrad, I did a fair amount of storm chasing. This is a tornado, the famous Red Rock tornado, April 26, 91. This is me with a lot less mass and a lot more hair. And this was an incredible tornado intercept that we did back in the days where you didn't have all the fun chasing tools that you did now. If you all of the OU students were on this storm. This is a famous day. This is the famous day of the tragic Andover, Wichita, and McConnell Air Force Base tornado that kind of went through there. Different tornado, different storm. There's a whole line of storms. This is one in northern Oklahoma. So this was basically an F4 tornado that we tracked on the ground for almost 45 minutes plus. Anyway, so yeah, I don't chase anymore. I chase vicariously through my students and via radar, because I've decided it's not fun to get the nice car beat on with hail. Anyway, okay, so that's just a little bit about me. Okay, so the speaker's charge that I was given to talk about today was to address the challenge of predicting the weather as seen daily, multiple times on TV from the meteorologist perspective with regard to climate change and its impact. Okay, so this is actually a pretty profound, especially the climate change aspects of this and the intersection of these two. Oftentimes, these two worlds don't directly interact. You think, I mean, they do obviously have a relationship, but anyway, this was when Sue sent this. I don't know if this was if you realized it was as deep as it actually was. I want to sort of first set the context for today's discussion on the climate side. So I'm not here to make the case for climate change. Okay, I'm basically assuming the consensus. So the consensus for the discussion today is the overwhelming consensus of the climate change community. So this is just a cut, a snapshot of the latest IPCC Intergovernmental Panel on Climate Change, the summary for the policymakers. But boiled down, so there's a thick summary for policymakers, there's a thick summary of the technical part, and then there's the full technical proposal. Boiled down, okay, it's real, it's bad, or it's real, it's us, it's bad. Okay, and you've probably heard that. I'm just gonna come here, I'm not gonna make that case, I'm gonna sort of assume it as we go forward. Okay, so just setting some ground rules here, okay? Let's see. Yeah, so what I'm gonna do is talk about forecasting, okay? And in particular, what I am going to do is talk about, spend some time talking about the development of one of the main forecasting tools that meteorologists currently use. And this is called the models, or numerical weather prediction. Okay. And then what I'm going to do, I'm going to talk a little bit about this and sort of bring in the challenges of predicting the weather, and then also then I'm going to connect it to the climate part of the speaker's charge, right? Why is this becoming more challenging? And try to address that too. So this is sort of a little bit of a two-part talk in some sense. Okay. So this begins back in the days of World War One with a fellow named Louis Richardson. And so he was a British physicist. He graduated from Cambridge in 1903. And he was a pacifist, okay? He was basically drafted into World War One. He was a pacifist, became an ambulance driver in a Quaker unit. So lots of downtime, lots of time of terror as well when he was actually out doing his ambulance duties. Pardon me. But he was an ambulance driver during World War One. He recognized early on that the atmosphere has to obey fundamental physical laws, the laws of fluid dynamics. And what he did in his downtime was to develop the first numerical forecast. He basically took a simplified version of the governing equations, the relevant equations, and attempted a 6-hour forecast over this region of Germany, of Europe. So that's Hamburg up there, and Vienna and Zurich. So of Europe. Okay. He did it for a 6-hour forecast. So like pretend you start the forecast, like pretend you know the weather at noon, and you're trying to predict it at 6 p.m. that night. So that's sort of what he did. It took 6 weeks to do this by hand via slide rule, just for these points on this grid. Okay. Excuse me. On its surface, it was a failure. Okay. The surface pressure, sort of blew up. Like it grew to an unrealistically large value, so again, on its surface, it was a failure. Subsequent, more recent analyses in the 80s and 90s kind of revisited his work and showed that the problem, it actually was sort of a success. He just needed to massage and filter the data first. Had he done that, it would have been successful. Okay, so this first attempt was something of a mixed success, but it sort of hinted at the possibilities. Then he sort of put on his, I don't know, maybe not sci-fi, but his sort of like dreaming hat. And he dreamed of, he wrote this article in the early 20s, dreamed of having this kind of setup, like a physical giant globe, where you had people, rows of computers that were people, sitting at all of these stations, doing calculations of these equations for their own points, and then talking to each other on the people just on either side and above and below. And then interacting with whatever person or people were up here on this central pedestal, relaying the information to them. And in this way, you could try to scale up his little effort. I think he realized, if you read this article, he realized that, you know, this was more of a thought experiment than anything else. But still, this is in some sense a metaphor of the way we do numerical models these days, and forecast models. Okay, now step forward 20 to 30 years. Okay, so we're in the sort of World War II, post-World War II era. This is the era now of the first successful numerical weather forecast. Okay, so this is a famous article, in my field famous, I guess, in the from 1950, and if you read it, it's fairly dense. The main thing I would like point you to is, for historical reasons, Jules Charney, very famous meteorologist, atmospheric scientist, responsible for a lot of theoretical advancement of the field in the 40s and 50s. And the last fellow on the list, John von Neumann, very famous 20th century mathematician, physicist, polymath. He worked on game theory. He had his hand in everything, and he had his hand in. I mean, I think he should be a household name with Einstein and the other Feynman and the other 20th century scientists. But he had his hand in this too. I point this out just because I have always found him fascinating, but also because, like it or not, the early history of numerical weather prediction is inextricably woven with the history of the bomb. Okay, the early computers were developed to do simulations of nuclear explosions, and von Neumann was kind of in that as well. Okay, so these early calculations were done on the ENIAC, kind of famous early computer that took up, there's a picture here, but maybe the size of this room, with 20,000 vacuum tubes and 1,500 relays, and those served, this was the pre-transistor era. Okay, so those served as the switches and logic gates that transistors and now little semiconductor chips do now. And it took like 200 kilowatts to run this, and it ran at 5,000 operations per second. So, I mean, this is like the early days of digital computing, but somehow they still managed to take a whack at these numerical forecasts, and then things have just kind of exploded from there. Okay, so now I'm going to sort of fast forward us again, and show kind of the basis. I'm a physical scientist, so you have to forgive. We always are tempted to throw in one sheet of math. Okay, you don't have to understand the math. It's okay. I just want sort of to know that these equations or equations like these form the basis of all sort of numerical prediction of the weather. Okay. Okay. And the reason I'm showing these are what are called partial differential equations. These are the laws of fluid dynamics. Sort of Newton's second law, sort of F equals ma, and conservation of mass, conservation of thermodynamic energy. Okay, so we have all of these equations. Again, don't worry about the particulars. These form the basis not just of numerical weather prediction, but also they're very similar to what you use in climate. They're similar to what any field that uses fluid dynamics is going to start with really fundamentally from the same place. Whether you do, I always joke that the chemical and mechanical engineers do molasses in a pipe. If you do molasses in a pipe, okay, or any kind of fluid dynamics. So this, or aerodynamics, if you're designing the airplane or Formula One car, you start in the same place, okay? And then you kind of manipulate them into a form that's more useful for you, okay? Okay, so this is what we start from, the really kind of scary looking math. And just to point out that this predicting the weather with computers is a series of basically physics and applied math, combination of physics, applied math, and computer science. So what we do, you can't solve those equations with pen and paper, okay? So we have to solve them on computer. One of the ways we do this is to basically break up the planet or a chunk of the planet and put a grid like this, points like this on over that grid, and we solve the equations there, okay? And we do this, again, on computers. At every point, we solve the same set of equations. This is something computers are very good at, lots of repeated calculation, okay? And so we have lots of points in the horizontal, and we have lots of points in the vertical too. So you can imagine this three-dimensional grid, either sort of regional or over some finite region, or over the globe, okay? And so we take the equations, we put them in a form that we can solve them here, and we then crank forward to make a forecast. To do that, to make a forecast of what's going to happen tomorrow, you have to start with what's today. So we need good observations of what the conditions are today. And so we do this with a wide range of observations from the surface and upper air, and ships and airplanes and satellites. So the surface observations, we have an official NWS surface station out at the Lawrence Airport, northeast of town. There's also a station in Topeka with the Weather Service office there. There are quite a few of these surface stations around. And then upper air, you'll notice there's far fewer upper air stations. So these are the weather balloon launches. We call them radiosondes. They're launched typically, operationally, they're launched twice a day. We would love to have more, okay, but they're incredibly expensive. This is a sizable amount of the National Weather Service, at least in our country, of the National Weather Service budget, is just making sure that there are twice a day balloon launches. So this is a gold mine, because this helps you understand the three-dimensional structure of the atmosphere. And then we have ship observations and aircraft. Okay. And then I'm not even showing here, but there are satellite observations too. We have to get all of these disparate observations into a way that can be ingested into the model. This is a field in and of itself. It's called data assimilation. It's a very challenging and interesting kind of little part of this whole enterprise. Okay, so we do that, and then you march the model forward. Okay, we do this typically on supercomputers. This is a fairly new. I think this was installed last year. This is one of the brand new supercomputers at the NOAA Center for Environmental Prediction, NCEP. This is one in Virginia. So they set one up in Virginia and one in Phoenix. So they've spread it out. They used to have them all back out east, but they started worrying about hurricane landfalls being disrupted. So they intelligently, I think, diversified the computing resources. And so we've, they have these in both places. And these run a number of different types of models. And we need different models because some of them are more short range, some are more long range. The different models are suited to different problems and questions that we can ask. And there's a lot, as I mentioned, a big part of this is computer science. There's science and somewhat of an art also into getting these problems to run well on cutting edge computing architectures too. And so this is sort of what it looks like. These are chilled rooms, computer rooms. We have a couple of these even on campus here at KU. But yeah, you've got to, and this is also too, if you, especially if you're just kind of used to running a laptop or a desktop, when you make these big computing centers, you may say, I want this much sort of computing. You also have to budget in power for that because it takes a lot of power to run these. And you have to budget in cooling for them. So this is something, if you've read the news about mining Bitcoin and all these things about building huge AI, all the artificial intelligence computing centers that are building out in the desert or wherever. There's a huge sort of water and energy footprint associated with these, and that's true of this enterprise as well. Okay, so what does this look like? This is a lot of, like, I showed some horrible math. I've shown some really intimidating looking computing. What does it look like? What's the output look like? They show computer model output on the evening news. I mean, if you've seen animations of how they think the atmospheric state is going to change over time, this is what it looks like. It looks like map data that any of us can interpret. So I've just plotted here. This is just a 60-hour forecast from a few years ago. Well, 2011, of basically surface temperature. Okay, just as an example, you can slice and dice any variable, any field you want to see: temperature, pressure, wind, humidity, etc. Okay. So you can either look at maps like this, or you can look at what the forecast model says is going to happen at your particular location. Okay, and this isn't some closed druidic enterprise, right, where only those in the know have the access to this stuff. This is all, especially for the American models, this is all easy to get. Okay, any of these websites, you can go and look at model output to your heart's content. The Europeans historically have been a little bit more guarded with their data for reasons. They have their reasons. But our model output, you can go and look at it and also download it and just use it as you see fit. Okay. So I want to talk a little bit here about some of the challenges. I've kind of just sort of painted a broad outline of how these systems are developed. And I'll eventually get into a little bit more how forecasters, sort of how forecasters use them. Okay. I want to talk about some challenges, and this is a little inside baseball, but I'm just going to hit the high points here, not go into all of the nitty gritty. But sometimes it's easy enough to show all these beautiful maps, and I'm mostly like in my own research work. I'm mostly what's called a modeler, so I do lots and lots of numerical simulations. I get too airsick, so like going out, I'm not good at the observational side or going out and flying through in airplanes through storms. So I do mostly computing simulations. We have so much computing power at our fingertips nowadays that it's easy. You can make really beautiful plots. It's easy to fool yourself into thinking that, oh, this is reality, because sometimes it looks as pretty as reality. So you have to take a step back and realize, no, this is not reality. This is some truncated, simplified representation of reality. Okay, that's always, anytime you do models, weather models, climate models, etc., you always have to keep that in your mind. So model shortcomings. This is, for any forecast model, is going to have this. Oftentimes, I showed you the whole kind of blood and guts math, but oftentimes we filter and simplify the equations to something that's a bit more tractable and solvable even on computers. Sometimes we leave processes out. Usually we leave processes out that we think we can get away with leaving out. Okay, we're not explicitly going to exclude something that's important. But sometimes, usually that works. Sometimes it can come and bite us in the rear afterwards. We always want to run, you remember the grid that I showed? Usually, like, you think, oh, I want that as fine as possible so I can know exactly what's happening here and, all the way to Topeka and Kansas City and north and south. The more points you have, the more expensive it is computing-wise, because you're solving all that math at all those points, okay? So we have to make a call on how many points we can have based on our computing resources. There are issues with terrain. Okay, if you're kind of have points only so far, and if you've been to the Rockies, you know how complex terrain is. It simplifies how realistic you can make the terrain. And then this last one, this is an area that I actually work on. If you think of those grid points, okay, what I showed was a typical weather grid. For climate, climate models, it's even coarser. A lot of times you might have grid points only every degree of latitude and longitude. And if you kind of close your eyes and think about that, and then think about individual clouds or even individual thunderstorms, you're going to have there's a lot of stuff that's going to be going on that's inside that grid that you're not really able to represent by those coarse grid points. Yet it's important, right? You want to know if there's that single thunderstorm may give you a lot of rain or not. You need to be able to represent that. And so there's a whole kind of subfield of the discipline also devoted to what are called parameterizations, okay? Dealing with these processes that are happening on scales smaller than what the model can resolve. So I predominantly deal with the sort of 4A. I do a lot of work on cloud physics parameterizations and how aerosol cloud and precipitation, sort of the interaction between these three. Okay, but these are some of the challenges that we have to deal with. Again, this is not reality. We're trying to come up with a sort of representation of reality to learn about the processes, and then learn how to develop tools to be able to predict the weather. We also have issues with data. Okay, this is a challenge with the other sort of side of the coin when we talk about numerical weather prediction, is how to handle the data, because you can imagine the better data you have to start your forecast, the better the forecast is going to be. So we have issues of sort of the spatial density of data. If you remember, think back to the slide where I showed land and ocean and surface and air. Like, we have lots of good surface observations over land, okay? Over the ocean, upper air observations over the ocean are much sparser, okay? So we don't have an even distribution of observations over the Earth. And this sort of has implications for how good our forecasts are, okay? There are errors in the data. We have instrument errors. We have different types of instruments, even for measuring the temperature, for measuring the moisture. There are issues of sampling, okay? A lot of these we may be, you see these data points are supposed to be representative of a large grid, but usually we take these measurements at a point. If we're using satellite data, a lot of times the measurements are representative over some area. All this stuff has to be squared away and understood before you can kind of implement them in a model that's in a way that's sort of useful for forecasting. And then there's sort of processing uncertainties and errors as you try to gently shoehorn these into your model, so you can have a good point to basically start with. Okay, so it's always good to be. In science, we try to advance the field, advance knowledge, but we also try to be sober about what we're doing and sober about the kind of understanding of the strengths that we, and the weaknesses, and so, or challenges. Okay, and these are some of the challenges. That being said, forecast models have greatly improved over the years. And this is for a number of reasons. We get faster computers, okay? And I didn't really say this is one of the reasons I got into the field. I grew up in Oklahoma, so I was really interested in storms and really interested in computing. And so this is kind of, I really enjoy the kind of computational side of things. So we have greater computer power. It's really come a long way. That enables us to use kind of more complete equation sets, okay, that better represent the fluid flow. And along with that, sort of better, when I say numerical methods here, I'm basically talking about more sophisticated mathematical ways of going from that really horribly intimidating equation set to something that the computer can use as a forecast. And it allows us to use more sophisticated, when I say physics here, more sophisticated representation of cloud processes, okay, or land surface feedbacks, okay. And then more and more data, satellites, okay. And so, and I mentioned ensembles here, I'm just gonna briefly mention that. This has kind of been sort of the rage the past 10 years or so, 10 years, maybe not plus, but about sort of 10 years ago. If you run a single model, you get sort of one representation of what the forecast will be. For reasons I'm going to mention here, it sometimes is beneficial to run a bunch of slightly different, a bunch of forecasts starting from slightly different places. This gives you a lot, it's called an ensemble. This gives you a lot of information about how much confidence you should have in the forecasts that you make, okay? And sometimes I've even seen some ensemble plots on the news in the last probably 3 or 4 years, and I'll kind of mention that here in a minute. So this is, the ensemble is a little bit, I may have gotten cart before the horse a little bit here, but a big part of, I'm going to sort of defend the meteorologist here a little bit. A big part of the challenges of in meteorological prediction are these intrinsic limits of predictability in a flow that permits turbulence, okay? So the idea here is, even with a perfect model and error-free observations, you go out and measure the temperature perfectly, etc. Forecast error is going to grow with time, okay? There's a deterministic limit to the predictability of the atmosphere and the ocean. And this is what we have to fight with. That theoretical limit is around 2 weeks, is kind of the current, I think, consensus estimate. The range is shorter for smaller scale phenomena, and it increases for larger scale waves. I mean, when I say smaller scale phenomena, you can be even ridiculous and just think of a plume of smoke and like think of like trying to make the prediction of the evolution of that, and you realize that it's going to the predictability limit is going to be very, very short. So here's a little kind of schematic of what this sort of looks like. So we have time and temperature. So you start off 3 forecast models. Say this is temperature at a given point. Start off 3 forecast models with slightly different initial temperatures. And you can see that for a while, they're going to kind of generally be happy together, and then they're going to run off, okay? So this is being sort of highly sensitive to initial conditions is what we call this. And this is a property of a chaotic system. And so this is sort of the kind of more pop way of this is sort of the butterfly effect, okay, in more sort of pop language, or one sort of like manifestation of the butterfly effect. Okay, so this is where I defend the meteorologist. In spite of these challenges, our forecast models are getting better, okay? And so this, like, we all like feel persecuted when people say, oh, meteorology is the only job where you can get things wrong half the time or most of the time and not get fired, okay? Right, so this is in a weird kind of, this is sort of like plotted as a correlation. So the idea here is 100% is good, okay? So we have sort of improving forecast confidence going from all the way back to 81, all the way to 2013 for kind of 3-day, 5-day, 7-day, and 10-day forecasts, okay? We're still struggling at 10-day forecasts. If you ever see somebody promising you a snowstorm and snowstorm amounts 10 days out, you can like safely just ignore it. I mean, you might be, the best you can hope for with that much lead time is that the larger scale pattern may be in such a configuration that there's a possibility that might happen. But be very skeptical of those really kind of snake oil type promises that far in advance. Okay, now I want to talk a little bit about how trained meteorologists approaches forecasting. Okay, so they typically, like a typical NWS forecaster, is going to have a background, maybe with a meteorology or an atmospheric science degree, background in the math and physics of the atmosphere. So like a degree, and they'll, in the sort of meteorology curriculum, they'll take classes on like learning conceptual models of weather and storm systems. Typically, we do this a little bit, but then when they go to NWS, they'll get training in a wide variety of forecasting tools, and then a lot of training. What they're trained to do is to combine sort of this physical understanding of the atmosphere, a great degree of pattern recognition, which is something humans try to do sort of anyway, model output forecasts that I was talking about earlier, and then knowledge also about model misbehavior, okay? These models all have biases, and these biases are oftentimes like situationally dependent. And so this is part of the meteorologist training, is knowing when you can believe the model and when you can't. And then they throw all this together and issue a forecast, okay? And so this is sort of like, I mean, this is like a forecaster, like all of what they do into one, how many, 5 bullet points. But there's a lot of work, a lot of training involved. I do want to say also that there were forecasters before numerical modeling, okay? So I don't want to say that, the famous like D-Day forecast in 1944, that was sort of before the days of numerical modeling. But numerical modeling has brought about sort of a revolution in how forecasting is done. Okay, so I'm going to revisit this point here before I kind of transition into the much shorter, kind of more climate-y part of the talk. Revisit this, but I want to look at the ways that climate change can have an impact on meteorological forecasts. Okay, this sort of climate that's warming, it's becoming more extreme, etc. What implication does this have for forecasts and forecasters? Okay, so I want to talk just briefly about a few items, kind of ranging here in order of sort of maybe a more obvious consequence to a warming and warming climate, and then to maybe things that are a bit more subtle. Okay. So this is one, and there's a lot of work going on in this area. This is not my own area of expertise, but I do know some of these people on some of the articles, and these are some of the a few of the articles that I pulled out. One of the consequences of climate change is the greater likelihood and frequency of extreme events. And flash flooding being one of those. Okay, and the kind of theoretical underpinnings of this are that, like, basically this is sort of theoretically sound, and it's been I think pretty well observationally established in climate models. Water vapor tends to increase about 7% in the atmosphere for every degree of warming. Okay, and that's quite a bit. And so you have more moisture in the air. Any precipitation events that you have the possibility of becoming more extreme. And so this is the kind of the basis of this. This list here these are a bunch of hydrologists who've looked at some climate model output of various quantities and stuck that into their hydrological models, and have come to the conclusion that yes, this warming is sort of going to lead to more greater frequency of flash floods. Usually, I think the point here in their paper is not necessarily more in terms of frequency of storm events. It's largely that the storm events that you have will be shifted toward more severe amounts. Okay, so this is one. The other, we were talking earlier beforehand about hurricanes and the risks of being on the coast. This is sort of an important one. This is written by several years ago by one of my super famous colleagues from MIT. This is some guy that got his PhD in 2 years, which is just like makes me like, yeah. Anyway, so what he did, he's done a lot of hurricane work, especially theoretical hurricane work, for a long time. And he basically used a suite of climate models to provide sea surface temperature, which is the main factor governing hurricane strength, plugged that into a simple analytical model he developed. And then he did a lot of these statistics, and he basically showed that his findings suggested that a storm that intensifies, so this is about rapid intensification of hurricanes. So a storm that intensifies 60 knots in 24 hours before landfall, that sort of in the 20th century occurs maybe once per century, in a warming climate is going to occur every 5 to 10 years, so be much more frequent. Okay, so these instances of rapid intensification are going to become much more common, and this has really sort of profound implications for where we are in hurricane forecasting. Because generally speaking, the experts at the Hurricane Center, the NOAA Hurricane Center, do an admirable job of forecasting hurricane path. Okay, but intensity is much harder. Getting good forecasts of hurricane intensity is much harder, and this is because there are all sorts of internal processes in hurricanes that sort of processes called like eye wall replacement cycles are one example of this, that really make this a challenge. And so adding this kind of enhanced possibility of rapid intensification to something we already just kind of do in a so-so way is pretty daunting. Okay. So this is we're getting a little bit more kind of in the subtle kind of inside baseball side of things. This is a horribly opaque title in terms of like what the heck does that mean? But really, this goes back to talking about this intrinsic predictability of the atmosphere. And what this group did was go and do a bunch of their own large-scale model kind of experiments, and looked at what the predictability limit was for those simulations. And what they found is that if you, for every 3 degrees of warming, which 3 degrees is basically the kind of standard, if you double CO2, 3 degrees is kind of the consensus of what the expected warming will be. they basically found that predictability, like the ability to make a successful forecast, falls by about a day. Okay, and this is pretty profound. The implications for this, like, not only is global warming sort of bad in terms of impacts, this is suggesting that it's making our forecasting enterprise more challenging and making forecasting itself less predictable. And this is something like totally outside of our control. This is just kind of an intrinsic property of the atmosphere. On the flip side, oh, where did it go? Hold on. On the flip side, we have this paper, which also is sort of opaque. This is, I mean, opaque, the title is unhelpful. But it turns out that this is a study that looks at one of the main waves of tropical variability. So the MJO is called the Madden-Julian oscillation. It determines a lot of the sort of what's going on in the tropics. Okay, so it's this 30 to 60 day wave that kind of moves from west to east, starting in the Indian Ocean, all the way across the Pacific. And it's important not just in the tropics, but it's important because it actually substantially influences weather where we are up in the mid-latitudes. And so this actually says that, hey, and by similar kind of methods to those previous studies, the idea here is that in a warming climate, these oscillations are going to become more pronounced and also more predictable. Okay, and so this is actually maybe a very small sort of glimmer of like hope that, okay, some things may become a little easier. Some aspects of forecasting in a warming climate may become a little easier. I think it's a net more on the making things more challenging side, but this is sort of an interesting article. Okay, finally, last bit here while I finish up. I want to talk about sort of what's the sort of ongoing or incoming sort of revolution of artificial intelligence for weather prediction. This is something that is it's not even on the horizon. It's sort of already happening, and it's kind of talking about it is all the rage. You can build an artificial intelligence machine learning model that can run on your laptop and give pretty credible forecasts. You can run it in 10 minutes and it'll give sort of pretty credible, at least out to a few days, forecasts. And so we've got lots of people working on this. It's been commodified, so there's lots of money in it, which I think is actually, personally, I think that's one of the reasons driving it. We have lots of scientific articles on this. Okay, so it can do okay sometimes for medium range forecasting, okay-ish on extreme precip. This is sort of, yeah, maybe. And then, though, this is the big one. Climate change could stump AI prediction, okay? And the reason for this is tied to how these AI models work, okay? They work fast on your laptop. You can run them on your laptop. They work fast because they're built on the shoulders of giants. They're built on these physics-based models that I ran us through. So basically how they're done, you need a training data set. And so you use 40, 50, 60 years of hindcasts from these physics-based models that are kind of observationally constrained to what the observational, like the real state was. You put that in, you run that through your AI, you get basically then the AI model is basically, in some sense, and this is a very naive way of thinking about it maybe, but it's a statistical regression. It's a statistical model to where then you can feed in new information and then it will march it forward and tell you what the weather forecast will be 6 hours a day, et cetera, out. Okay. It's only as good as what you're training it with. Okay. And the main implication, so there's lots of sort of deep implications here about statistics, about extreme statistics and tails of distribution. The main thing here that we're concerned here as far as climate change is you're training it with the 20th, essentially, predominantly the 20th century climate. And it doesn't know about what hurricane paths and flash flooding is going to be looking like in the future. And so it's not possible. It doesn't have the information in its model to be able to make weather predictions in that kind of environment. So this is a huge concern with these models. And it might be fine for a day-to-day. Is my picnic tomorrow going to be okay? Is it going to be 75 degrees or is it going to be 82? It might be fine for that, but it's not going to be able to pick up on the kind of more disastrous, like flash flooding event, hurricanes, et cetera, kind of signals. That's the concern here. Okay, with AI.
Probability based.
Exactly. Yeah, it's all a bunch. Essentially, these models are just statistical. Ultimately, comes down to a type of statistical model. Okay, so I'm going to finally wrap up here, and give a couple minutes for questions. Okay, to address these changes of predicting the weather. So hopefully I've kind of brought you through how these, at least the numerical models, the background of those, how forecasters use them, and then a little bit of how things might change in a changing climate. So, I mean, the one thing that came to mind when I saw this initial charge was do forecasters think about climate change when they're making the forecast? And I'm going to say probably not. Usually you're in the field, it's your shift, you're probably, especially if you're doing one of the nighttime shifts, you just kind of make the forecast based on what's in front of you. I don't think typically you're going to be making huge, having deep thoughts about climate change, but the climate change is all in, the warming, moistening, et cetera, is all baked into what you're doing. So it's, it cares about you even if your mind isn't exactly on that. And so with that, I'm happy to end here. Sorry, a few minutes late, but I'm happy to field any kind of questions you have. Yeah, did you? Yeah.
Blows my mind just thinking